I'm Chief Commercial Officer for Quera, and I'll be the MC for this session. I'd like to introduce Dr. Ashley Montanaro, co-founder and CEO of Phasecraft, and he will spend the next 15 minutes with us talking about his amazing company. Thank you.
Thanks so much, Yuval, for that kind introduction. Yeah, and so good afternoon, everyone. I'm indeed going to be trying to take this opportunity to take a few minutes just to tell you a bit about what we're doing at Phasecraft, the quantum algorithms company, and also maybe a little bit about why we're doing it. Because, I mean, this is going to be very much a sort of really sort of big picture, sort of bird's eye view kind of talk. There's not going to be much in the way of scientific results, though I'm very happy to discuss this further with any of you that would like to know more about these. But really, this is the first time that I've been to QWC, and it's a sort of maybe an opportunity or an excuse for me to introduce Phasecraft to you and maybe say a little bit about why we think that what we're doing is interesting. Okay, so I think the starting point for my talk is going to be the sort of really big picture, right? Like, why are we interested in quantum computing? So I think probably everyone in this room is here because they're excited by the promise of quantum computers. So quantum computers could solve incredibly important problems like modeling materials for better batteries or better solar cells, maybe better catalysts. They can solve incredibly difficult problems in the blink of an eye, which our best classical supercomputers would take years to solve, or maybe thousands of years. And they might even help us make a significant impact on, systemic problems like climate change. So this is really an incredibly exciting technology, and probably many people here would agree. But on the other hand, I think it's also apparent that quantum computing is a technology that faces a number of challenges. And I guess the key one of these is that today's quantum computers are still very small, very noisy. They're beset by errors. The best quantum computers we have today are of the order of hundreds of qubits and can execute thousands of operations. Whereas if we want to get to full quantum fault tolerance and implement arbitrarily long computations, then we may need to have ultimately millions of physical qubits to achieve this. And we already saw this morning that this is on many hardware companies' roadmaps, so we think that we'll get there eventually, but it's still a massive challenge to face for us. And so this is why, even though it does sometimes feel like we're really living in the future when you think about the world of quantum computing, it also sometimes, for me, feels like I'm still living in the 1950s. Because, back in that time, things in many ways were similar to what they are now. So the world's best physicists and computer scientists were trying to develop these amazing new machines that were pushing at the boundaries of what was thought to be possible with the laws of physics. These devices were still incredibly small, incredibly resource constrained. They weren't able to execute, today's incredibly bloated software that might need trillions of operations. You could execute almost hundreds or thousands of operations at a time with some extremely sort of targeted hardware. And I think, it's sort of funny to think, okay, this picture here is actually not a quantum computer, even though it may look like one. This is the memory unit for the UNIVAC computer. And this could store, at most hundreds of bits in a mercury delay line. So, but back then, these machines were, just like today, incredibly resource constrained. And there were amazing breakthroughs that were happening every day in the development of this technology. But what I think is often forgotten is that the technology on the hardware front was happening in conjunction with the development of the algorithms to operate that hardware. And a nice example of one of the first sort of algorithms that was run in that time period in a sort of in a non-military context is this example where these first machines were used to compute the result of a presidential election, which may be somewhat topical. And in fact, the UNIVAC predicted that the Eisenhower would win an absolute landslide, which surprised everybody, including the programmers of the machine, because they didn't even build into the software the ability of having a third digit looking at the chances of success. So you can see it says chances are now 0 to 1 instead of 100 to 1 for the election of Eisenhower at that time. So this is an example of one of the sort of first algorithms that was run at this time, but it's far from the only one. And there are many other brilliant examples. So if we look back even earlier, like in the 1940s, this is the ENIAC computer, which is the predecessor to the UNIVAC, and it was used to simulate the dynamics of nuclear reactions. But this would not have been possible without the amazing algorithmic developments of John von Neumann and Nicholas Metropolis and others who invented the Monte Carlo method for randomized computation. And this is a method that's actually really dear to my heart because many years later, I came up with a quantum algorithm that speeds up this method. And going back even further still, like this is showing the hardware that was used to crack the Enigma code in the Second World War, and this would not have been possible without the Banburismus method that was developed by Alan Turing at that time to use this hardware ultra efficiently. So if we go back to today, I feel that the analogy is pretty clear that we ought to put as much effort into developing the algorithms as we are developing the hardware. And that's exactly what we're doing at Phasecraft. We're developing the quantum algorithms that are going to get the most out of today's quantum computers alongside the world's leading quantum hardware companies who are developing the hardware on which these algorithms are going to run. So I'd like to just say a little bit about how we're doing this and the kind of problems that we're working on. So I'm going to start by talking about a problem in materials science. So this picture is showing the material strontium vanadate, SRV03, which is an exciting potential candidate for next-generation battery cathodes, as well as other applications. And it's also a material where, if you want to model it classically, standard methods based on density functional theory, or DFT, completely fail. And so it's an interesting candidate for tackling via modeling on a quantum computer. But if you look at the best algorithms that were known at the time that Phasecraft was founded, the number of operations that you would need to run on your quantum hardware to model that material was of the order of hundreds of billions. So this is clearly far beyond the capabilities of today's quantum computers or even the sort of quantum computers we're going to have in a few years' time. So this seemed to be very much intractable for today's hardware. So we started thinking about how to solve this problem more efficiently, and we developed a full pipeline that goes all the way from a description of a material, such as strontium vanadate, through to a quantum circuit for modeling that material. And it puts together a host of different ingredients, which together enable us to get really significant reductions in the cost of that modeling problem. So these include material science, where we're selecting the key aspects of the material to model using density functional theory, quantum information, representing the system in an efficient way for modeling and running on the quantum computer, and also the efficient quantum algorithms themselves, developing new ways of modeling the time dynamics or the sort of low energy state preparation that you might want to do for this physical system. And then ultimately the measurements at the end, you need to get useful information out for some properties of interest of this material system. And these ingredients are all put together in our materials modeling pipeline, and this graph shows the impact that this had. So if this y-axis is showing the number of operations as represented by the number of quantum gates that quantum hardware has been able to perform over time, just looking at one particular hardware family of platforms. And the green line is showing the complexity that you need for actually solving this modeling problem. And the algorithmic developments we managed to come up with at Phasecraft were enough to bring this problem to really within touching distance of today's quantum computers and well within range of quantum hardware manufacturers' roadmaps over the next few years. And the improvement that we managed to get was, in fact, a 43 million-fold reduction in the number of gates that you need to model this material. And this is not just for this one material. In fact, there's a whole, there are dozens of these materials where we were able to apply this methodology, and you can see all of these on our website, materials.phasecraft.io. But sort of amazingly, like this 43 million-fold improvement, this is not actually good enough, right? It's not good enough for us, because this is still putting this slightly beyond the realm of today's quantum computers. So in order to sort of cross that last bridge and try to get to the complexity of something that could run on today's machines, we took a step back and thought about how things are actually done classically. And classically, the standard way for modeling materials is density functional theory, DFT, which is shown in this pipeline here. So it's an amazing idea which was responsible for a Nobel Prize, and it's really the workhorse of materials and chemicals simulation. And in fact, most of this idea works really well for most materials. The one bit which does not work well is the bit where it tries to handle the quantum correlations in a materials or chemical system, which is just one small component of this whole tool chain, but it's one where classical methods really struggle. So what we were thinking was, can we replace this part with a quantum algorithm instead? And that's exactly what we were able to do with quantum enhanced density functional theory, or DFT. And I just want to show you some results for how well this performs. So this is looking at the low energy states, the ground state of the notorious Fermi-Hubbard model for superconducting systems, and this is showing a 1 by 200 system. So it's a 1D system of size 200, which is far beyond the capabilities of today's best quantum computers to solve directly. And this is showing like what the shape of this density looks like if you use standard classical DFT. And this is actually completely wrong, this picture, because what you should see is these shoulders in the plot, which are representing a mix of conducting and insulating behavior. And this is only seen classically if you go to a specially fine-tuned version of DFT, which uses the knowledge of the exact solution of this system in advance, so it cheats, to be able to basically write down the solution exactly. But remarkably, quantum enhanced DFT is able to reproduce this picture and also pick up the correct physical features of this system. And this will be able to extend to 2D and 3D systems where the classical method does not work anymore. Okay, so we're really excited by this. And I think, it's important to say that when we're developing algorithms, we're not doing this just theoretically in isolation. We also are actually running our algorithms on real quantum hardware. And in order to do this, we're having to develop novel error mitigation techniques and other ways of really getting the most out of what's very limited quantum hardware today. And a nice example of where we were able to do this is an experiment together with Google a couple of years ago, where we implemented the world's most complex low-energy quantum simulation of this Fermi-Hubbard model on their world-leading quantum hardware. And because of the error mitigation techniques that we developed, we were able to execute 10 times more gates than the best previous experiment and use 4 times as many qubits than the previous experiment was able to do. So this was really exciting validation that these techniques are actually working in practice. Thanks. And it's important to say, like everything I've said so far is talking about what we can do in the near term with quantum computing. But these algorithmic techniques are not just useful now. As the hardware gets better and better, then they're going to get more and more out of that hardware. And in general, it's always better to make the performance of the algorithms as good as possible, to reduce the complexity of the algorithms, because it just means you can do more and more on the hardware, and as the hardware gets better, you can solve more and more challenging problems. And it's also key to say that, getting to quantum advantage within a few years, as opposed to, say, 10 years, as maybe other people might say, is not just a sort of interesting theoretical thing or something that would make a quantum physicist excited. Like, it actually means a lot of important things for humanity in practice. It means things like discovering novel battery materials using quantum computers years earlier than otherwise. It means things like developing new drugs using quantum simulation far sooner, with obviously huge impact on human health worldwide. And it even means the efficient solution of problems beyond ones where quantum mechanics seems to play a key role, such as the solution of hard optimization problems using a quantum computer, for example, optimizing an electricity network so that it becomes more efficient and everyone's energy bills are cut down. So that's the sort of problem that we're working on. And we're working together with some of the world's top quantum hardware companies to implement these algorithms on their hardware so that we can get to this point of quantum advantage as soon as we possibly can. And we couldn't do this without our amazing team. And this is a picture of the Phasecraft team as of the start of 2024, when we had offices in Bristol and London in the UK. This is a picture from our company retreat back then. But today I'm sort of very pleased to be presenting our new Washington, D.C. office just down the road, which is led by Professor Steve Flemire, who's right here. I'm going to get him to stand up, actually, just to embarrass him further. And Steve has already put together an amazing team of distinguished quantum scientists, some of whom are here today, actually, at the conference. Maybe you'll have a chance to speak with them, to really start building building Phasecraft's US Center of Excellence. So we're really excited to now be based here in the US as well, and hopefully this will be a great opportunity to speak with many of you in future. So I guess this is everything I wanted to say. So I guess I'd just like to end with this message, which we genuinely believe, which is that beyond just developing amazing quantum hardware, it's absolutely key to develop efficient quantum algorithms because that's what's going to unlock quantum advantage. Thank you.